Okay, cool. Yeah, thanks everyone for joining the day. This is the Seoul Rust meetup. Yeah, welcome everyone. Today we're going to we'll have some just like sit around and talk around the table, of course, too. But like the main thing for today is going to be a presentation on building cross-platform mobile SDKs in Rust. This is something that I've been doing for work, and I thought it would be fun to kind of walk through some of the cool stuff we did, some of the interesting challenges and whatnot of using Rust as the core for a mobile app. So I guess we can just like dive in and get started with that, and then like this can be like pretty interactive. Like if anyone wants to say anything, you got a question or whatever, then just talk or say something on Zoom. Feel free to unmute yourself. My name is Ian. I've been a iOS developer since 2008. That was actually my first like real programming job. My first passion was doing mobile apps. Mostly due to the luck of timing, me being a sophomore in university at the time when the iPhone was released. So that was just kind of lucky timing. I've also been doing Rust since 2018 at my current company, Stadium Apps. We've been doing that in production since 2018. And yeah, I'm currently the co-founder there. My partner Luke is in Switzerland, and I'm here in Korea. So apologies in advance. I am really terrible at drawing things. So this diagram is like, it's terrible. No reservations about that. Yeah, boo. Yeah, thanks, Calvin. So the problem that brought this whole thing up, and the reason why I'm giving this talk, is because I wanted to build a mobile navigation SDK. And there's a lot of reasons I could talk about why I wanted to do that, but we'll just leave that as the background for now. And I want to build it so that it works on both iOS and Android devices, and maybe even some embedded stuff in the future as well. Who knows what new platforms are going to be feasible in the future. So I wanted to have the core logic to be written in something that was shared. Because the basic process of figuring out whether the user is, for example, drifting off the route, what the next maneuver is, the instructions to give, all this kind of thing is very shared. It's not a platform specific behavior. So I decided to do that in Rust and use this you call like hexagonal architecture, if you want the buzzword. Some people call it ports and adapters. It basically means that there's these layers, and there's clearly defined interfaces, API boundaries, if you want to call them that, that everything is communicating to. So the core, for example, is not talking directly to the GPS on your Android or iPhone or whatever. That's having to go through a couple of layers. So like your iPhone, for example, is going to have its own location services running, and then it's going to be pushing that down through the layers into the core of it, which is then going to make the business decisions. So for example, with the case of GPS, if my phone gets a new GPS update, then that's going to flow first through the native code and then down through to the Rust, which will make a decision like, is the user still on the route that they were supposed to be on, or do we need to take some action like display a message or do like a voice prompt. So that's kind of the architecture of it. I'll put these slides out, like publish them somewhere later as well. So if anyone wants to go back and look at this, then you can. So there's a couple of interesting problems with building something like this. The first one is having bindings that work and feel native to a developer who's writing in Swift or Kotlin. So the iPhone developers are going to want something that feels native to them. They're not going to want this like crazy, like calling a C function or something like that. And the same with Kotlin or Java developers on the Android side. and generating idiomatic bindings for Swift and Kotlin to Rust code is a little bit of that's actually a pretty big challenge.
Is it generated or do you write it?
It's generated, and I'll talk about how in a bit. Yeah, good question. Same with compiling and linking for multiple targets is interesting. You might think like, okay, like when you're just building Rust on your machine or for a Linux server or something, then that's pretty straightforward. You just like run cargo build, and it's like most stuff is x86 or ARM if you're on a Mac. But on like for Android, then there's like 4 different CPU family targets that you have to worry about, and there's 2 on iOS. So gotta do a bit of that. And then the most complicated part actually is not the bindings generation, the compilation part, but actually shipping a library with the wrapper to end users. That's actually a little bit more complicated, and we'll talk a little bit about that towards the end and the challenges that we had. So you're asking Calvin about how the bindings are created. I'm not writing these by hand, fortunately. There's this really awesome project from Mozilla called Uni-ffi. I think that's how they pronounce it. Uni-ffi, yeah, whatever. Sorry, anyone from Mozilla. Yeah, and so it's open source, and it supports Kotlin, Swift, Python, and Ruby. I'm actually kind of surprised at the Ruby part. Yeah, I'm actually really curious what the use case is. It's like Mozilla actually built this for Firefox Mobile, and Firefox on the desktop. So like if you're using Firefox like on your MacBook or whatever, they actually have Rust in some of the core in Firefox, and they need that to talk to other pieces of Firefox. And the same on mobile. So they wanted to take this, of course, on desktop, and it's fine. Like it's C++ and Rust. Linking together is pretty easy. You don't need that much like scaffolding. The mobile side though is challenging. So they actually wrote this whole project to do the binding generation so that they could use Rust components common in Firefox Mobile and Firefox on the desktop. To make things a little bit easier and to have clear boundaries, they have this thing called a interface definition language, and that specifies what is exported. I'll show a little bit of example for that later, actually. Actually, why don't I just go off script and
functions or
show a little bit. So it exists in a single file, this UDL file. And so like, for example, if I wanted to export enumeration of error types, so like one of the errors when we're trying to create a routing request is that you didn't give enough waypoints. Like you can't create a route with just like 1 point. You have to have at least 2. So you can specify your enumeration variants this way. These things called dictionaries, these would be structs in Rust. They would be, I believe, data classes in Kotlin, and just regular classes in Swift. And then you can define interfaces. This would be for like callbacks, which we can talk about a little bit later. And
so one question.
Yeah.
So if you just write this UDI file, it'll automatically convert what you have here to Rust.
Hey, welcome.
Yeah. Bindings for this?
Yeah. First, welcome. Thanks for joining. Sorry, it's probably a bit hard to find. Yeah. So the way that this file works is it doesn't generate the Rust code. You still have to generate the Rust code yourself. So like, let's go back to that enum variant really quick because that's an easy one. So I'm gonna search for this. Where's the definition for that? So you can see the usages in the UDL file. And then here's the actual definition. Like it's just you actually have to write the Rust code yourself. What it does is it generates the Swift and the Kotlin code for it. Does that make sense?
Okay, so in that file you define it.
Yep. So basically I define this has to look like this. There has to be a type exported from the library that looks like this. It has to have this name and has to have these enum variants.
It just looks for that name of the enum.
Basically, yeah. and then it will generate Swift and Kotlin code for that, and Python and Ruby if you're doing that. Yeah. I'm really curious who is actually using this with Ruby. But yeah.
I'm super curious because we have some Rust code that we want to write bindings.
Yeah.
To actually Node and Python.
I'm kind of surprised they don't have JavaScript that. Well, I guess yeah, and you could do node bindings, yeah. Yeah.
Would it generate?
Well, this project doesn't do it, but I'm just saying it's conceptually possible to do node bindings. Yeah. So like actually I think I've copied this. I think we can actually look in here and see.
The node binding library is actually pretty good for Rust. It's quite easy to use.
Is there some
Yeah.
library that does that?
It's a Simon wrote a library and it does a lot for you. It's very it's quite.
Is it also to do that?
The API. I can't remember. I remember it was quite easy to use. So.
Yeah, so like here's the like the FFI like this is all like FFI generated code here for this. Yeah, here's the so you can see this is actually completely auto-generated Kotlin code in this case for those enum variants. Like you've got not enough waypoints, JSON exception, unknown exception, and those match what you see in the UDL as well as what's in Rust. And you can see, by the way, as well, like we've got these error decorators. I believe it's this error that it uses. So like you can see that ended up translating as well. It's somewhere in here that I forget where exactly it is, but yeah, that all ends up getting passed through basically. So your error messages even go through. So that's pretty nice. Yeah. So yeah, Uni-ffi, or however you say it, actually feels like kind of magic. Like the generated APIs are actually really idiomatic as they promise. And it even supports a variety of system types. Like I was kind of surprised that it has timestamps as well. So like you can actually use like there's like a system time trade in the standard library in Rust, and then it will get converted into like a Swift date and a Java date and all that stuff. It also generates protocols or interfaces in addition to the concrete types. And that's super nice because it lets you do mocking and stuff really easily. So that makes it really easy to test your code. It also even has support for native callbacks with the interface implementations. So this is super cool because you can basically define an interface that's like, so in your UDL file, and it's like in your UDL file, you're going to say like, okay, I want this interface that has like a get secret method or something, and it's going to talk to like the keychain on iOS, which is their secure credential storage APIs. So then on the iOS side, you would write some Swift code that talks to the keychain libraries on iOS, and then all that you have to do is implement this interface, and then your Rust code can take advantage of the native stuff. And in our case, since we're building a navigation SDK with it, then the cool feature is that it allows users to bring their own routing implementation. So a user could do something like have their own like offline route generation. So if they're shipping some local information that they've downloaded with their app, then you can do like custom offline routing or whatever you want. Any questions so far on that? Yeah. Cool. So how do you actually do this? So I think that this is probably not the ideal way, and there probably is going to be something better than a build script at the end of all this. But for now, we're just using a build script on iOS. It's literally a shell script that does cargo run. You have to actually call the Uni-ffi bindgen. You actually have to like define this like extra binary target in your workspace and everything. It's a little bit annoying. They haven't published it like an official version on crates.io because it's not stable yet. It's only version like 0. I forget what it is, but it's pre 1.0. So yeah, you run the cargo command to say, okay, I want Swift output, and I want it to go in this directory. And then I just move stuff around so that it's like I'm using this model repo structure. So it just moves it to the right directory. And then we build a framework with it later, which we'll talk about. And then similar on Android, although in Android, it's actually a little bit easier because you just define a build task inside your Gradle script. So basically, instead of having to write a separate shell script, it's basically a shell script that's embedded in there, that whole command line thing. Oh, and I forgot about that. I actually even compile the code directly in Gradle, so I don't ever have to run that build script manually. The automation on the iOS side is not quite as good yet, but that's how that works. And here's a quick example. Sorry, the Zoom thing is totally in the way for everyone here. Let's see if I can fix that. Get out of my view, then run that. Yep. So this is just some basic Swift and Kotlin code. The Kotlin one's actually a little bit easier to read, so I'll focus on that one. But basically, this route adapter type is something that I've defined on the Rust side. And I'm saying create this new HTTP routing instance and passing a string to it for the URL, and then another one for the profile. And it's really easy. They make calling out idiomatic as promised. But it's not all perfect. There are definitely some challenges that we ran into with Uni-ffi. One is that you have to have all the exported types visible at the top level. So like you have this like weird, this weird structure in like your lib.rs where you have all these like imports that don't really make sense, or you just like throw a bunch of stuff in there. So it's a little bit annoying from a management perspective when you're trying to build a library that the whole point is to export most of it. Also, bizarrely, you don't have to declare things as public. It's actually able to import private stuff using the UDL. I don't know exactly how that works, but yeah. There's also not very much documentation on how that UDL file is they have like really basic documentation of it, but it's not totally complete. There's a lot of holes in it. You're also not able to split things into multiple modules or use multiple UDL files at one time. It's like you have to put everything in one file, and that's it for that library. If you want like a separate library, like you have to make like a separate crate and a separate UDL file and all that stuff. Similar to the documentation problem, the errors are completely useless. If you like make a mistake, like if you forget a semicolon or you misspell something or whatever, then the error messages you get back are not helpful at all. So it's pre 1.0, but like it's very rough. And then like I said a little bit earlier, it only generates the bindings. It doesn't actually help you with the whole packaging of it, which is like a separate problem. So some tips that I have from working with this. First one is to use the generated protocol and interface types as much as you can, because the big benefit is that you get easier mocking, so you can write unit tests against it. So for example, if you're building a navigation SDK like we are, you don't want to have to rely on having an actual like GPS signal in a device in order to run a test. So if you're doing everything through interfaces, then you can create all of those types with mocks or similar things in other languages. The kind of rule of thumb, which they actually put in their documentation, is to always pass the protocol or interface. So when you're like writing a function that accepts something, don't accept the concrete type, accept the protocol, so that way it's generic and you can test it easily. And then when you're constructing something, obviously use the concrete type. There's also a third-party plugin for doing syntax highlighting in the UDL files. I can show that. A rough edge of it is like it actually is not very good at finding stuff. Like it tells me that this thing doesn't exist, but it works. Like this is totally fine. This file works. It gives a lot of like false errors, but it does give you syntax highlighting, and it does tell you some of the obvious errors. Like I think if I get rid of this semicolon, then like, yeah, it'll be like, probably like expected semicolon. Yeah, expected semicolon got dictionary. So it definitely helps with these things, because these errors, even though it's like kind of broken, these are way better hints than the generator will give you. Yeah,
This is not a language, it's like a.
oh, it is, and it's like a domain specific language. I mean, this class of things, like they call it UDL for Uni-ffi definition language.
So the data structures mainly, right? You just
Yeah.
defining data structures.
It's data structures and interfaces. It's like a header file.
Yeah, and function calls.
Yeah,
So does it generate Rust code too?
it does not generate Rust code. It generates well, I mean, it actually does generate some Rust code for Glue.
How do you link your generated data structures with Rust code?
So when it runs its generator, then it checks to, so it generates this like glue between like it generates like all the FFI code for you. So you don't have to write that yourself. You're not having to go and write like manual like FFI. You're not having to write unsafe code or anything yourself.
Do you need like style?
Yeah. Yeah.
You need that. Exactly. Name.
This type has to exist.
Okay. So name's gonna match.
Yep, it's got to match exactly. So it's in error.rs, and you can see this matches exactly. There is this enum, so it has to. So there has to be this enum exported, and it has to have these three variants. Like otherwise, it's not gonna like pass the binding generator. It's gonna like say like no, not liking that. And then additionally, where is it? I think it's like lib.rs. You also have to make sure that you use it in here. Where is that? Yeah, you have to make sure that you use that. And so I don't even think I use that type. Yeah, okay, this is a great example. So like what I end up doing is because otherwise I would get like a bajillion errors, like I just pub use the type, even though I'm not gonna like use it anywhere else. So what that does, that says I'm officially like exporting this type. So the compiler will not say this is an unused import. Even though, right, like I guess like someone could actually consume this crate in the future. Like I don't actually expect anyone to be writing Rust stuff on top of this crate. I expect it to be used only for mobile. So I don't really need to export these with pub use. But I do, because it makes the compiler happy. I don't get as many like stupid warnings.
You can use it for any domain. It's not just for mobile, right?
So it was designed kind of with the mobile focus. So it's Swift and Kotlin, but it also does Python and Ruby.
Right. So you can use it for any project.
Yeah, absolutely. Yeah. I'm just using it for mobile because that's like my particular use case. And it's what they made it for. Like they made it for Firefox.
There's a Firefox.
Mobile
always.
Yeah.
And it's still maintained, still being developed.
Yeah, it's being very actively developed. Let me like it's updated. Yeah, the last update was yesterday. And they do releases pretty frequently. Do they have
Might add some more languages, I guess, like Node.js is pretty.
Yeah, I don't know why they don't have Node. Maybe it's because there's already good.
The one that exists already is actually really good.
Yeah.
Existing Node.
Oh, I guess I need to imagine they don't have a nice metadata in Mozilla. Come on, guys. Yeah, I know it was last updated 2 days ago. So I guess you can update to about 24.2. Yeah. Oh, but yeah, the tangent we got on here was this UDL file. So this actually, it's like a class of domain specific languages called interface definition languages. Like this is not the only language of this type. Like it's like a thing in language theory, like interface definition languages that just exist to define the interface. So that's what this is. It's like a C header file. It's just the
programming languages.
Yeah. Other weird thing is you can't have mutating struct methods. So all of your objects are defined as structs, and you can't have mutating methods on them. So what you have to do instead is you have to use these interior immutability patterns. So I'm not sure this is the best option, but I'm currently using the standard library's mutex type. Because everything has to be both send and sync. So you can't use a lot of the other ones, like one cell, for example. You can't use that, even though it's designed for interior immutability. I think the thing with one cell is it's not thread safe. So I think it's not send. Yeah, anyways, that's just like an annoyance. So if you have like we model a state machine basically in the core, and we want to basically, like, that's a classic use case for mutating struct methods, and we can't do that the normal way. So we just fake it and use a mutex to make sure it doesn't blow up. Safe.
State machine is quite nice.
Yeah, right.
Yeah, I
very good
experienced
for
that
us.
machine when I was using Rust.
Yeah.
I really liked it. It's like
Yeah.
this.
Yeah.
Did you use a library? You just wrote your own?
I just wrote my own for now, because the states are very simple in the navigation.
Sort of works with writing state machines. Like
It's use the type system.
Yeah, it seems to work.
Yeah, like this is like this is still pretty early, so it's definitely not. This is not the complete state machine, but like right now, there's basically two states. Like you can't initialize the navigation controller without routing information. So there is no like pending state or whatever. That's all like in the mobile application logic. All the messy HTTP stuff, that's all in the mobile app. So there's basically two states. There's navigating with our current status, like the last user location. That's like the raw, the one that's snapped to the route line. The actual, like the full route, which isn't going to change unless you need to recalculate, and the remaining waypoints. That's what we currently have. Like we'll probably add some other ones as well, like dynamic estimated time of arrivals, things like that. But like that's pretty much it. And then we use IS, and this is like the thing that defines the transitions. And then inside the navigation controller, yeah, we use mutex because Uni-ffi doesn't handle mutating struct operations very well. Actually, I put more notes in here than I did in my presentation. Nice. Others like ref cell are not enough, as the entire object has to be both send and sync, and ref cell is explicitly not sync. Yeah, that's the problem with that. And then so there's the constructor, and then the interior mutability stuff happens here. So like the core operation and navigation engine is going to be like, you get a new update on the user's location, and then you do something with that. Like either like you're going to say, okay, we're going to move along here to like the next step, or whatever. Like this logic is not complete yet. It's basically a bunch of to-dos, but that's like if you've arrived at the location. So it's basically the state machine right here, and instead of doing a mute, then we just wrap everything in a mutex lock. Oh no, his keynote froze.
They're like a sort of a hello world thing, where you can just, can you write a binding for like hello world from Rust to Python?
Right now, I don't think I could do that right now. This project actually, if you want to see that though, actually, what? Okay, first let me uncrash keynote. It's not hard, it's just a lot.
Sounds like a lot of, to be honest, yeah. Boilerplates?
A lot of boilerplate, but you know what we can do. I literally pushed the first commit to this is like what I thought was the minimal like hello world basically. It was an adding. It's basically the Mozilla example. Yeah, world's most elaborate hello world. Okay, let's talk through this. Get ignore not interesting architecture. Yeah, I'm basically giving you all this right now. Screw that. Auto-generated crap. Oh yeah, those are that's a auto committed code from the template. Okay, here's the actual demo. Okay, so all that's generated code. So let's yeah, the core is all generated in this commit. The interesting stuff is actually in the demo app, and it's in yeah, let's check the main activity here. So Yeah, here's, okay, so let's back up a second. Okay, so you can see it's basically all boilerplate. This is the first important line. We're importing uni-ffi.ferrostar.add. So it's literally importing like the add method. And then here we're creating like a UI block that basically is like a text blob that says, hello, name whatever's passed in. Rust says 2 + 2 equals, and then it adds 2 + 2 using 2 unsigned integers. So that's the Kotlin side. This all rest of it is going to be just auto-generated crap because thanks Java.
That's the Rust code.
Yeah, that's what I'm getting to next. So the Rust code, what you have to do is, okay, that's just the workspace, sorry. So the actual cargo.toml is really simple. Basically, the only thing that's important is the actual dependency and then the build dependency on Uni-ffi. Build.rs is just imports that basically says generate this. This is what says generate the Rust FFI code based on that UDL. The UDL is just one thing. It's a add method that takes 2 unsigned 32-bit integers and then returns a unsigned 32-bit integer. Here's the actual library. It's just adding 2 numbers and returning the result, what you would expect. And then there's a quick unit test for it. So that's it on the Rust side, as far as the actual like interesting code goes. The rest of it is all generated by this.
So it also takes a look at the arguments, not just the.
Yes. Yeah. So if you change this to like U64 or something, then it's not going to compile. It's probably going to give you a useless error, unfortunately. And then on the Swift side, we've got this. So I just have like a high-level wrapper here that calls add, and then I don't even know if I had a user interface in this version. Oh no, there's the content view. Basically the same thing as the Android side. Basically just use that core object and then called add. So it prints hello world. Rust says 2 + 2 = 4. Or Ferris says. Reasonable enough. Hello world. Anything else you're curious about in there? Yeah, like seriously, most of like the stuff that I actually showed you is really the only interesting stuff. Like this is like that's just like auto-generated. Actually, that actually is a useful unit test. I did actually have a useful unit test for this one. Yeah, 2 + 2 = 4. That's literally what I did. That's the unit test.
So you wrote this.
Yes, I actually did write this unit test. Yeah, because it does not generate unit test.
It might be useful for like languages like Python. It's like that 1+. I don't know if you're like using floor.
Yeah.
You're depending floor. Like the 1 + 1.5.
Yeah.
1 is 2.
Yeah.
Yeah, it'd be 2, not 2.
Yeah. But you would have to. That's like a very specific thing. So I don't know if you could reasonably generate those. Yeah. So cross-compilation. This is actually surprisingly easy. So first a little bit of the top file, the Rust toolchain.toml. I actually learned about this while doing this project. I didn't know about this before, but you can if you add this file to like your cargo workspace or whatnot, then you can say which channel you want. So like stable, nightly, that kind of stuff. And then you can also specify which targets you want to use, because that saves the user from having to go and cargo install or rust up add or something like that to add all these other targets. So like the first 4 are Android and the last 2 are iOS. So Android has a couple of different ARM-based targets, and then i686. That's actually kind of funny. That's actually kind of funny. And then like 64-bit would be for like the emulator. And then same story on the Apple side. You have the 64-bit ARM, which is the actual devices, and then you have the x86 simulator. That unfortunately is a different target, and that has its own complications, which we'll talk about later. And then basically all you have to do is call. Oh yeah, and then you'll actually notice that the targets are actually slight. So that includes like the broad targets, but then you actually have the specialization that happens So like in the AR64 Apple iOS, then there's the simulator as well as the device, because they're actually separate platforms, even though they're the same CPU architecture. So like my MacBook is M1, so that's an ARM-based architecture. So it's not like the same family, but there's a specialized target. Yeah, so the generate FFI function, just to explain the shell script a little bit, that's calling the Uni-ffi bind gen, which takes the UDL file and generates the FFI glue code, as well as the bindings for Swift in this case, and then creating the simulator fatlib framework. We'll talk about that later. Android had a few quirks. So Apple platforms are they go way back with C-based languages. So historically, Apple used a language called Objective-C, which was a superset of C, similar to like C++, but not as annoying. And so it's really easy to link a C library with an iOS app. But it's not that easy on Android, because Android is all Java based, and with Java then you have like NDK and JNI. NDK stands for Native Development Kit. JNI, I believe, is Java Native Interface, which makes things a little bit easier to work with nowadays, but still not easy. So you need to set some stuff in your local cargo config.toml with the exact linker paths for your specific native development kit. For some reason it doesn't automatically find this stuff by itself, probably because with Android you can actually have multiple versions. In fact, it's quite common to have multiple versions of it installed, and for reasons then most Android developers don't just always use the latest, which is what's typical on Apple platforms. So this is a bit of annoyance, and I found a really helpful blog post that explained all of this, which I'll link in the resources at the end. It's actually shipping the library. So we've got something compiled. We have a high-level wrapper, which is pretty straightforward, but a few quirks. Then you have to actually put that all into a binary and package it for each of the two platforms. Today we'll only look at iOS because I actually haven't gotten like as deep in the packaging process on Android, and I understand the iOS side better. So let's just jump into that. So first set of quirks is with Swift itself. So Swift actually is interesting in like Rust. Then you can do this nice like where were we in the lib.rs? Yeah, you can just do this nice like pub use thing, and even if it's not in your own crate, you can actually like publicly export anything from any crate that you've depended on. That's super nice, and yeah, it makes things really easy. However, in Swift there is no officially sanctioned way to mark a type for re-export. So where this is a problem is if I import something from the generated FFI bindings in Swift, I actually have to find some wacky way to re-export that if I want it to be accessible from another piece of code down the line. I can use it in that library. So like I've got a core library, but if I wanted to build another library, like, so the way we're doing it is we have the core, and then we have a UI layer, which is optional. And the UI is going to be distributed in a separate Swift package, because not everyone wants to have the entire user interface. Someone may want to use their own, they may want to use a different map library, something like that. So instead of forcing them to do that, we want to expose all this. But if you're going to do that, you can't construct these types from the outside, and you can't even reference the type anywhere. It's really messed up, actually. So like, even though I've got this function that returns like a route, in my Swift code that's like 2 layers removed from it, I can inspect the result as a return type. So like I can say like let foo equals this function that returns a route. But I can't actually construct a route. I can't say let with a type associated with it. So I can't say let, blah route equals foo. I can't specify this is an actual route. I can't even accept it as a function argument. I can't unpack enum variants, like, but the type is still there. It's just you can't actually use it for anything. So it's this it's a big problem with Swift. So what I ended up having to do is end up making these like dumb wrappers. Let me actually pull one up. That's the easiest way to explain that. Model wrappers. So for route, so what this lets us do is I now have a type route that I can use in something downstream, some package that depends on this package. And then I've exposed like a helper here. And then there's this inner attribute. This is accessible. So if I need to get any properties of the route, then I can, do route.inner, and I can actually like, I have the whole code completion. I can like get the properties on that. But this lets us actually use this in an argument somewhere. Like we cannot use this as a function argument. We cannot store this in a variable or anything in code without this. So that was a really bizarre Swift limitation that we ran into. It's a Swift problem.
Oh.
It's not a Uni-ffi problem. It would work if we had everyone additionally depend on the binary itself, but like that's it's stupid. Yeah, it's a Swift problem. It's not a Uni-ffi problem. Yeah. The next iOS quirk was building they call it an XCFramework, or stands for Xcode framework. So this is Apple's native format for distributing a binary framework from multiple platforms at the same time. The quirk with this was that the iOS simulator is one platform, but it needs multiple architectures associated with it, both Intel and ARM. So all iOS devices are ARM, but the simulators can be either ARM or x86. And if you try building an XCFramework with all three of the binary variants, then it will yell at you and it'll say you have two binaries for this platform, because it's like what is it like x86 Apple iOS. It's saying that that's like that's one platform. So what we have to do instead is we use this on line 43 in the little snippet. We use LiPo, which is this thing that's basically designed to smash a bunch of binaries of different architectures together to make what's called a universal binary on Apple platforms. So basically it takes all three of those and puts them, or it takes these two variants in this case, because they're both simulator variants, and or this the simulator, and then the it is both the simulator variants, sorry. And then it puts them together in one file, which then you can use to generate the framework. Otherwise, it'll only work on ARM or something like that, which is not what we want. Then with SPM, which is the Swift package manager, local development was a bit of a challenge. They have this so let me show you like a package.swift file. This is like their equivalent of like a cargo.toml. So in the Swift package, you can have dependencies, you can have targets, you can have products. It's like not like nothing rocket science about it. But for doing the binary target, which we reference here in the targets, which is how you reference the actual like Rust code, the framework. If you use this path one to do a local reference, this has to be a local path, and if you have another Swift package that depends on this package and you're also trying to develop that locally, then it doesn't work. This only works like one level deep. It can't be like exported to dependencies, so local development was really annoying. I did end up figuring out a way around that by I was trying to develop them as like two totally separate Swift packages, but what I had to do is move them into one package with multiple products. So the UI actually had to move into the package. Otherwise, local development was like impossible. I would have had to actually upload it to like GitHub or something as like a zip archive and then download it from there. That's the only way that you can reference them in a stable manner. The local paths are not usable for dependencies of your package. Silver lining though is that you can still make Swift changes and reference master plus your old release framework artifact in track main. You just can't touch the Rust lib. So if you have to do this, I found a way that I don't have to do that by putting everything in one package. But if you do have to do this, as long as your Rust code doesn't change, you can actually make changes in like your Swift or your Kotlin code or whatever. And you can still reference the old one. But yeah, I spent way too much time on that. That was like 3 evenings of work to figure all that out. So bring it all together, it does actually work. This is a screenshot of it all running in Swift UI and getting a route from the server and then drawing it on the screen. So it's still very early, but it all does actually work together. A couple of open questions still. We haven't figured out what the best repository structure is yet. Right now, it seems like the mono repo approach is actually best. And I'm not someone who normally has liked mono repos in the past, but I think it actually does work pretty well for this. Build system, like right now, I'm just using a bunch of shell scripts, particularly on the iOS side. Like I've looked at things like Bazel, they seem really complicated, but it would. Yeah, we'll see. It's still, that's what I've got like as an open question. I don't know if this is the best way to do this or not. And then on Android, I really haven't explored all the edges as far. So I feel like I've got a pretty good handle on what the problems are, where the rough spots are with iOS, but not on Android yet. So probably going to run into some more of those later. And then yeah, I'll put the slides up in like the meetup group as well, and so you guys can get these links. But the Uni-ffi user guide, link to the IntelliJ plugin that I used for the syntax highlighting, that Android blog that I mentioned about how to do all the NDK linker settings, and then a link to our project, which is open source navigation. Yeah, any other questions or comments? Cool.